To another physics tutorial. Today we'll be talking about the properties of friction, and we'll be looking at a problem revolving around that notion. So let's jump right in. Alright, so a slide-loving pig slides down a certain 29-degree slide in twice the time it would take to slide down a frictionless 29-degree slide. And the question they're asking from that information is, what is the coefficient of kinetic friction between the pig and the slide? So for this type of problem, I recommend drawing a free body diagram, and specifically for this problem because it's asking us to analyze two systems, a frictionless and a friction system. I've drawn two free body diagrams, and I suggest you do the same. And now I've already drawn them here with all the components labeled just to save us some time, but let's go through quickly and explain them. So right here we have the pig as represented by this block here, the mass of the pig. This angle theta is the inclined slide, and we know that this angle right here can also be theta because of trigonometric convention. Right here we have the normal force perpendicular to the plane, and here we have the gravitational force which is perpendicular to the ground. Now we can split up this gravitational force in relation to the normal force with the trigonometric components, which are as follows in relation to this angle theta. Right here we have mg cosine theta, and right here we have mg sine theta. So, and now here's the frictional diagram, which is all the same things, except instead we have this frictional force which is acting against the the pig as it slides down the ramp. And now the component of each of these forces which is causing the pig to slide down the slides would be mg sine theta as a result of this gravitational force, because the system of the normal force and mg cosine theta is 0 in both cases. So first let's take a look at the frictionless model, because it's a simpler model. And what we can deduce here is that the forces acting on this in relation to the plane give us that F net is equal to this component right here, mg sine of theta. And I can simplify that by writing mass times acceleration, because of F net, is equal to mg sine theta once again. However, the masses will cancel, and what we're left with is that the acceleration of the frictionless system is equal to gravity times the sine theta. And I'll abbreviate this in the next one, which we can solve for this because we have these components. I'll abbreviate this as F friction minus less is equal to, and plugging in, we get 9.8 times the sine of 29 degrees, which is approximately 4.75113 meters per second squared. So there we've solved the acceleration of this pig in this frictionless system. But they're asking us for the coefficient of kinetic friction in the it comes from this frictional system. So how do we start off solving the equations in this friction system? Well, we're given a key piece of information in the title, and that is that it takes twice the time to slide down the friction slide as it does the frictionless slide. So knowing this, we can relate that time to the acceleration, and what we can basically deduce is that the acceleration of the frictional system is equal to 1/4 times the acceleration of the frictionless system. So by solving this, because we have this frictionless acceleration, we get that the acceleration of the friction system, I'm sorry, that looks bad, we get that the acceleration of the friction system is equal to about 1.18778 meters per second squared. So now with this acceleration, we can solve for the kinetic friction force, the coefficient of kinetic friction in this frictional system. So we can write the equation of motion again as F net is equal to, again, mg sine of theta, which is this force here. However, now we have this friction force, this kinetic friction force, so we subtract this frictional force, which, and I should actually simplify this for us, which I should help you remember if you forget, that the kinetic friction force, Fk, is equal to mu k, the coefficient of kinetic friction, times the normal force, which in this case is mg cosine of theta. All right. So we're subtracting, in this case, mu k mg cosine of theta. So I can simplify this again, and I'm going to do a little bit of simplification on both sides. F net can be written as m times a is equal to, and I'm going to pull out an mg from these guys. So it's mg times the sine of theta minus mu k cosine of theta. And here we have our, we get our masses to cancel, like so. And the resulting equation is the acceleration is equal to gravity times the sine of theta minus mu k cosine of theta. So now we need to solve for mu k, the coefficient of kinetic friction. And what we can do that is simple algebra manipulation, which I'll rewrite this equation in terms of mu k, which yields that mu k is equal to acceleration divided by gravity minus the sine of theta divided by the negative cosine of theta. And evaluating this for A equals, right here, 1.18778. This is just plugging in values. And for gravity is equal to 9.8. And for theta is equal to 29 degrees. We get that mu k, this value mu k, and I'll rewrite it over here. So evaluating this in a calculator, we get that mu k is equal to approximately, let me just quickly do this calculation. We get that mu k is equal to about, let me 0.416, about 0.416. So that, this value right here, this value is the coefficient of kinetic friction for this system. And so we've effectively solved this equation of motion in this sense by using the information given to us in the frictionless system, relating the accelerations, and then plugging in and solving. So I hope that helped you out with your physics problem, and check back later for another tutorial. All right, have a great time.